sitting outside just drinking my coffee, and I saw not one, not two, but 3 huge possums walk right along the edge of my fence. And it started me to think about how many of these possums are in my neighborhood? Or worse, how many are gonna be in my neighborhood in like 5 years? So I looked up some things. I Googled how long is the gestational period of a possum, and how many of these little babies do they have every time they have babies. So I did some calculation. A female possum has 1 to 3 litters a year, so I'm like, okay, we'll take the average of 2. And then I started to figure out that they have 20 babies, but not all of them live. So about 8 to 9 of them live per litter. So I'm like, okay, we'll be conservative and take 8. So, and I also was like, okay, out of these possums, only the females are having the babies, right? So if I saw 3, we'll say only 1 of those was a female. And I'm starting to do the math to figure out how many possums there's gonna be in 5 years. So on average, I figured, okay, each possum is having about 8 a year, taking into account that only the females are having babies, they're having 1 to 3 litters a year, and 8 to 9 of those babies in each litter are surviving. So I started to figure out that this is a geometric sequence, and that's what we're studying in class right now. So I'm gonna take those 3 possums that I saw and see how many will there be. So here are the 3 possums that I saw. And I'm estimating approximately that they will multiply at a rate at 8 per year. So the next year, I will have 24 possums. Okay, so there are 2 rules that we can use to help us figure out what's gonna happen in the future if we know that they're multiplying at a rate at 8. So the first one we're gonna have is the explicit rule. A sub n means any number in the sequence. So that is the number of possums that we are going to see. A sub 1 is how many we're starting with. So in this case, it's my 3 possums. R is the rate, which is they're multiplying at a rate of 8 possums each year per female possum. N sub 1 is the number in the sequence. In our case, this is gonna be years. I'm gonna see in the next year how many more possums are gonna be. So this is one way of writing the rule. So I could use this to figure out how many possums there will be in, let's say, 5 years. So if I wanted to do that, I'm saying A sub 5, meaning in the 5th year, I plug in 5 for n, and then I can plug that into my calculator to see how many possums I'm expecting in 5 years. All right, so I'm gonna type in 3 times 8. 5 minus 1 would be 4. So 12,288 possums in the 5th year. Granted, we know they're probably not going to survive in my backyard with that many, probably not enough food. I don't know. But theoretically, if they all survived, let's hope they don't, 12,288 possums, that's a lot of possums. The other way we could write this rule is using a recursive rule. In the recursive rule, what we do is we say A sub n, which represents the same thing. We start with our rate. It is multiplying at a rate of 8 times the previous term in the sequence. That's what this means. So we're taking 8 times the previous term in the sequence. And we're saying that we're beginning with the 3 possums. So this is how would we write a recursive rule. In order to use the recursive rule, we always have to have the previous number in the sequence. So it's not as helpful as the explicit rule, but the explicit rule is very helpful because we can jump straight to whichever number in the sequence that we want. And that's the power of geometric sequences. All right, let's try another example. Let's say you work for the CDC, the Center for Disease Control, and you notice that there is a lot of outbreaks of this new virus that is killing people. And so you start collecting data. You start wondering in the certain area, let's track Montgomery County, how many cases have been reported in the past 6 months, because you want to see what kind of pattern is going on. If you can recognize a pattern, you can know what's going to be happening in the future. So you collect some data for the past 5 months, and you notice this is the number of cases. It's definitely going up, but what is the pattern by what's going up? So in order for it to be a geometric sequence, that would mean it would need to be multiplying by a constant ratio in order to prove that it is a geometric sequence. So if I take this number and divide it by this number, if I type it in my calculator, 56 divided by 47, I get 1.19. All right, 47 divided by 39, I get 1.2. 39 divided by 32, I get 1.21. If I do 39 divided by 32, oops, I already did that one. 32 divided by 27, I get 1.2. It's 1.18. I'm rounding to 1.2. So I could even round this to 1.2. Notice it's very close to a ratio of 1.2. So because there's a constant ratio, I would need to multiply by 1.2 to get each subsequent term. I proved that this is a geometric sequence. So if this is growing at this rate, this constant ratio, I can now figure out how many people I expect to be infected in 2 years if this pattern continues. Obviously, I work for the CDC. We're going to want to figure out another way to get this under control. But this is our projection at this point if it continues at this rate. So 2 years, that is 24 months later, since I'm doing months here. Let's write our explicit rule. So if I'll write the generic rule. So A sub 1, the first month we reported 27 cases. They are multiplying at a rate of 1.2, which is a 20% increase each time. Now, if I want to figure out in month 24 how many cases of this disease I expect to find, if it continues at this rate, I'm going to plug 24 minus 1. So I'm going to type into my calculator 27 times 1.2 raised to the 23rd power if I subtract that out. And I am estimating 1,789 cases in only 2 years. This is obviously some kind of virus. We need to figure out a plan to get under control. Now, how about the recursive rule? In the recursive rule, I take the rate, which is 1.2, times the previous number in the sequence, and A sub 1, we are starting with 27 cases of the virus. Our last example is going to be about a particular kind of bacteria that splits in half every 20 minutes. If the scientist begins with 100 bacteria, how many will there be in 3 hours? So when we begin, he has 100 bacteria. So I'm going to label this, because my X is going to represent the number of 20-minute segments. We haven't had any time pass yet because he's beginning. So this is like at 0 amount of time. We are beginning with 100 pieces of bacteria. And if it is splitting in half each of those bacteria, every time it splits in half, we now will have double the amount of bacteria. So after one 20-minute section, I will now have 200 bacteria. After 2 20-minute periods, so now we're at 40 minutes, we will have 400 bacteria, and so on. All right, let's write a rule to help us figure out how many bacteria there'll be in 3 hours. So first, let's start with a general rule. A sub 1 in this case is going to be 200. Notice that's how it is after the first 20 minutes, is 200 bacteria. My rate, it is doubling each 20 minutes. So every 20 minutes, it's doubling. And this is times, we are doubling it up from the previous term. That's what this means when we do n minus 1. All right, so let's check our rule to make sure that it's working the way we expect it to work. So if this rule works, I should be able to get 2. When I plug in 2, I'm going to get 400. So A sub 2, and I'm going to plug in 2 for n. Let's just verify. I should get 400 if I wrote the correct rule. It's always a good idea to check your rule to make sure that it's actually working the way you expect it to work on smaller numbers. That way you know you wrote an equation that's effective. So 200 times 2, 2 minus 1 is 1, so that is 400. So that's what we expected to get, so our rule is good. Now we can use this to make our prediction. If we want to see 3 hours, remember these are 20-minute chunks, all right? So what I want to ask is how many 20-minute chunks are in 3 hours? Well, 20, 40, 60, there's 1 hour. 20, 40, 60, there's 2 hours. And so the third hour. So that means that there are 9 20-minute segments in 3 hours. So 9 is actually the number I want to plug in because there are 9 20-minute segments in 3 hours. So I'm going to find A sub 9 and plug that into my formula. 9 minus 1. So I'm going to type into my calculator 200 times 2 to the 8th power, which is 51,200 bacteria. So that's how many bacteria will be in 3 hours. Make sure to check your rule because that always helps make sure that you have a really good working rule before you start to answer the question.